Hi everyone, this is a weekly reading group where we talk with authors about their papers, happening every Monday on Zoom. You can join that yourself. It's just a link. The details are down in the description on our website where you find the link. And yeah, maybe we see you here as well. And now let's get into some subgraph representation learning with Haoteng. Let's go.
Thanks, Hannes, for the introduction. I'm Haoteng, the fifth-year PhD student at Purdue CS. I'm working with Professor Pang Li. So today, basically, I'm going to introduce our work on algorithm and system co-design for efficient and scalable subgraph-based graph representation learning. So this is a joint work with my colleagues at Purdue and supervised by my advisor. Okay, so in this talk, I first go to introduce what is the subgraph-based graph representation learning, its benefit over classical graph learning method, and the current challenge for its development. I will present the three novel subgraph-based frameworks for large-scale graph learning tasks through the algorithm system co-design. So basically, the first one, the SUREL, built the foundation of this line of work on efficient subgraph-based models. Then the follow-up SUREL Plus makes it more scalable. And I will also go over the recent work on hash-based MPN models if the time permits. So I will cover the basics also for the canonical. So the canonical models of the subgraph-based model for link prediction, like a seal, disease encoding, and labeling tricks. So there's no need to say that graph structured data nowadays are everywhere in our daily life. They capture the social relations on social network. It builds the connection between the users and the product and services, and also is widely used to formulate the scientific problems such as transportation networks, and they're presenting the proteins or molecule structures. So with all those availability of those massive graph data, graph learning algorithm and their applications have become a training topic. So based on how many nodes that involved, we can categorize those learning tasks on graph into three types. That is to decide the property of a node, whether there is whether there is a link or a relation between two nodes, or we want to classify a group of nodes. So graph representation learning is one of the most popular answer to answer those questions. So by mapping those graph structure data into a latent space. So, and then we apply machine learning techniques on top of it. Traditional graph embedding method and graph neural networks are two major family of it. So, but in the following, we are focusing on the multi-node task that are including like at least two or more nodes. So this is the core for applications such as friend recommendation on social networks and community detection in e-commerce. So recently, there's a new family of method called a subgraph-based graph representation learning. So instead of obtaining node-wide representations, so subgraph-based models to learn the representation of a subgraph surrounding the query here. So the example here is a link, like whether U and V are going to have a link over here. So it's first proposed by SEAL for link prediction, then it's formalized by distance encoding, and then generalized for multi-node task by the labeling trick. So in general, actually, all of the task applications on graph covered by today's talk can be formulated through representation learning on subgraph defined over here. So the key difference here is the subgraph-based models and the vanilla GN is that it actually learns the representation beyond the node level. We are focusing on the subgraph level. So basically convert it into a subgraph classification problem. So, but the first thing we want to answer here, why we should care about the subgraphs. So here is a toy example for friend recommendation on social networks, which is a core application for link prediction. So in this graph, is user A is more likely to be friend with user B or user E here. So as we know nowadays, the graph neural networks are the de facto tool for encoding the graph structures and node features through message passing, and then use the obtained node representations for this prediction. But here, if you observe closely in this example, the node B and node E are actually, they are in symmetry. So, and we observe that the unfolded computation subtree actually are identical in this case. So that is without distinct node features. If we use GNN, then they will map those two nodes into the same representation. So that will be leading to node user B and E have the same likelihood of links with user A. So this behavior would pose a very critical issues for GNN-based recommendation systems. And also, there are other works that show that GNN are limited for more than complex relations and high order patterns, and they have other limitations listed over here. So to address these issues mentioned of the vanilla GNNs, so subgraph-based models are proposed. For a given query here, it's going to first extract a subgraph surrounding it. So here we call this query-induced subgraph. This is the query is A and E. We want to know whether there's a link between A and E. Then for the same query here, we can find the difference between the GS1 and the GS2. So there's subgraph induced by query S1, A and E is certainly different from S2, A and B. And also, if you observe closely, you can see that A and E actually are 3-hop neighbors, and A and B are 2-hop neighbors. So they clearly tell the difference and avoid the ambiguity between them. Also, using the representation of the subgraph that consider the joint relation between the query nodes have more expressive power than simply concatenating those node-wise embeddings for multi-node application. It also addressed the entangled model depths and the resistance field, and also it showed the superior empirical performance on the OGB leaderboards. So we're going to dive in a little bit for subgraph-based model because it's basically the foundation of all the following works of mine. So in practice, the subgraph-based models are always paired something called distance-based features. We call this as a labeling trick. So these figures give you 2 examples of these features. So the left one is called using the distance encoding. So basically, it is using the shortest distance path from the center node to each target node in the extract the subgraph. And the right side using another labeling trick called double radius node labeling, which is simply going to add the shortest path distance for the target node, one target node and another target node. So they combine those 2 things together. So if you observe those 2 examples here, and you can see that in both cases, they will lead to different representations of the node W and node V, and also going to show you different subgraphs for the UW and the UV, of course. So in this way, we can avoid the ambiguity issues as we mentioned previously in vanilla GNNs. So as we can see that subgraph-based models bring more express power here, but it is also come with a price. So canonical subgraph-based models, including those 3 over here, are neither scalable or efficient. Because first, they need to perform an extraction for each query for the subgraph, which is very costly, and their intermediate result cannot be reused. Basically, for each query, you need to perform a subgraph extraction. Then the second thing is that the size of these M-hop subgraphs are actually irregular, and it grows exponentially as the number of the hop increases. So lastly, previous works on accelerating or optimizing GNNs cannot be directly used here because we now is dealing with the subgraphs. So basically, right now, the current subgraph-based model have very limited system support. So all those things motivated us to design more efficient and scalable frameworks for subgraph-based models. So this brings our first work of SUREL that makes subgraph-based graph representation learning more efficient. So what they identified, the bottleneck earlier, is the subgraph extraction with labeling. So by adopting the algorithm system co-design, we propose to break the query-induced subgraph here into multiple node level random works. So those random works can be shared across different queries and then significantly reduce the redundancy. And also to address the irregularity of subgraphs, we decide to use a fixed length of the random works and to regularize its sampled neighborhood. We also introduced an encoding technique, structure encoding technique defined on those sampled works called the relative precision encoding. So this is to compensate the structure loss, because from the subgraph to works, we're certainly going to lose some edges. So through this way, we want to preserve some structural information in the original neighborhood. So together, overall, we use the joint of those node level sampled works and its RPEs as a proxy to this query-induced subgraphs for the learning tasks. So instead of extracting subgraph for each query, as we said, the work sampling here actually is performed on the node level. So it can be reused and be computed offline and in parallel. So basically, for each node on the graph, I just sample a bunch of random works with fixed length and numbers. So this design actually decoupled the input of subgraph-based model from specific queries, which is much faster than subgraph extraction. And also the relative precision encoding here is introduced to encode the relative distance of the node regarding the root node here. So here I give an example, like I want to know the relative encoding of node C here because it appeared at the sampled work here twice on the second step. So it's encoding it 0 to 0. Give another example of node A here. It appeared in the last step only once, so it's encoding 001. So from those relative precision encodings, you can actually tell the nodes sampled here from the original graph relative to the root node. So as we know, we see is the first hop neighbor. So you can see that from here, the first element here is non-zero. So basically from this way, you somehow preserve the structural information of the original neighborhood in this encoding. So basically combine the sampled works and the relative precision encoding. This achieved the similar express power as the labeling tricks, which is more powerful than the vanilla GNNs. So putting it all together, SUREL first performed the offline pre-processing and in parallel. So that is to break the node level subgraph into a set of works and its corresponding RPEs. So then for given query here, it called the join operation online to concatenate the sampled works. So for query A and B, I'm going to concatenate the work from A and work from B together. And then we're also going to join their precision encoding. So basically, for the same node appeared in both A and B, I'm going to join their encoding together. So the C node for node A and the C node for B going to concatenate together, become 0 to 0 and 0 to 0. Okay, so after this process, we got so-called query level subgraph. It's basically previously we decoupled it to node level. Now we put it back together on the query level. Okay. Then we're going to use the neural networks to learn the joint query level subgraph and generate a representation for model serving of the target query. And we also adopt some optimization techniques like parallelization, memory management, and load balancing to make it more scalable and efficient on the last graph tasks. So next, we're going to evaluate our proposed framework and other baselines on two types of tasks here. There is the link prediction, which is to estimate the likelihood of a link between two endpoints of a given graph. This can be generalized to predict the type of links, such as a relation prediction on heterogeneous graph. Another is called a higher order pattern prediction. So this one is to predict whether a set of nodes will foster a cover edge in the future, which is referred as a hyper edge. So all the models are tested and evaluated through the Open Graph benchmark. So we select the 3 link prediction and 1 relation prediction dataset. Colab and Citation2 are other social networks for citation and collaboration. Also, we use the protein-protein interaction network. And the OGB-MAC is a heterogeneous academic network containing 4 types of nodes: paper, author, institution, and field. And they also extract the relations. For high-order graphs, we use tag mass, which is the tags applied on questions on the mass website as a hyperedge, and also the DBLP co-author, which is temporal network that have the co-authorship of the papers as a time-stepped high-order links. So as you can see, all those data sets have millions of nodes and edges that reflect the need of the challenges for real-world applications on the large-scale graphs. So from this table, we can see for link prediction that SUREL achieved around a 50% performance boost than traditional graph embedding method and the vanilla GNs, and also have a comparable or even better performance than previous SOTA model SUREL. For the relation prediction and a high-order link prediction, we achieved up to 60% improvement than standard or relation GNs, and they have even better performance for compared to the subgraph-based models, as they suffered from those scalability issues. So as for the scaling performance, SUREL can match the training time of vanilla GNs, but we also acknowledge that it's much slower in terms of inference. But however, we also see that the vanilla GNs can only achieve subpar performance on those predictions tasks shown on the previous slides. So within the subgraph-based models, SUREL achieved like 5 to 20 times speed up than SUREL on inference, and also it reduced their memory consumption by a half. Okay, so a quick stop here for any questions or comments regarding our SUREL.
None from my side. Anything in the audience?
Yes. I think Denise.
Yes.
Yeah.
I wanted to ask, like in the limit, this initially random walk-based embedding method, like positional encoding method, will it in the limit be similar to something like PageRank or like a kernel method on a graph?
Sorry, I didn't quite get the question. Can you say it again?
Yeah, my question was if in the limit this method would be similar to features extracted from something like PageRank. So yeah, I mean, clearly here you are very far from stationary distribution, I suppose.
Yeah.
Yes.
So basically here we try to do thing is like we try to so basically to introduce the concept that for link prediction or other multi-labeled, multi-node prediction, we need to model the joint relationship between them instead of to capture the single node embedding, then put them together to make it work. So at 4, the way we achieve it, like using random works, is just a way to make it more efficient and scalable. And the link between, I also going to mention about a PageRank in my next work that we actually bridge them together.
Okay, and the second question, I'm just a little bit murky about what you mean by the query. How many nodes a query contains in itself? Is it a query on 2 nodes or many nodes?
Okay, so here we just give an example of a link prediction. So link prediction is just contain 2 of nodes, but it can be, we also have this high order pattern prediction task that the query contain more than 2 nodes. So in this example, we give a 3 node. Like we observe the pairwise relation between 2 nodes. We query whether those 3 nodes together going to have a hyperedge.
Okay, and just final question. If, for example, a query would be between 2 distant nodes, would your algorithm suffer from maybe like some kind of maybe scaling issue or maybe something else? Because I'm not quite sure how you sample this random works along a distant path if expressivity will fall, for example, or maybe any other.
So basically, I give the 3 on the case, the 3 node case here is we sample the random walk starting from V1, V2, and V3 separately, like individually, offline in parallel. And then we came a query, we put the sampled works of V1, V2, and V3 all together. So it's decoupled from the query.
Okay. Thank you.
Okay, just. Then I guess we can go to the second work. This is a follow-up. Yes.
Just a minute. What was the time complexity like for the SUREL?
Okay, so for the time complexity is the work sampling. Basically, it's the number of works times the steps. And then it's not a traditional GNN model because it's now we just have those sequences. So we just use the RNN or LSTM for encoding those sequences.
Okay, thanks.
Sure. Okay, so the follow-up work is called SUREL Plus, which is further push the boundary of subgraph-based models. This time we can deploy this model on a billion-size graphs. So as we know that SUREL achieved substantial efficiency improved by decoupling the subgraph extraction, but it still faces several of inherent drawbacks of this work-based representation. So first thing we observed here is that, so among those sampled random works, we find over 55% of those nodes are duplicated. So this causes another issue is that we need extra space and also computation on those repeated nodes in work joining and neural-based encoding in the subsequent routines. And also we have a high workload of data transfer between CPU and GPU, so because of this. And secondly, because we are using random works, it's random, you cannot control it. So basically it gave us very limited control over the sample neighborhood. And also they may introduce some non-necessary neighbors. So one straightforward way actually is to address this issue is to reduce it from the work representation here to a set. Because first, the set naturally avoids those node duplications. So we only maintain the unique nodes appeared in the works. And secondly, we can actually here use any samplers instead of a random works. We can use a PageRank-based, for example, and also we can pair it with other type of structure encoders, like structure feature encoders over here. So, but however, this kind of a new idea based on node sets introduces several challenges. So from the algorithm side, because we first transaction from the subgraph into downsampled works, and then we further reduced it to sets. So basically lost all the link information over here. So so the problem here is that we need to develop an approach that can compensate for this loss while maintaining the empirical performance. And secondly, from the system side, because SUREL uses works, they can be easily stored or processed in a line format. We can control the length and the number of work sampling. But node set is different. They have irregular sizes. So those irregularity can cause great challenges for the storage and also the access of them. And also we need to perform online joining later. So for those serving those queries. So in this regard, we present a SUREL class. So this is the first set-based framework for SubGraph-GRL. So here is a side-by-side comparison with the previous SGRLs. So a little bit of recap is for subgraph-based models, it's first going to extract a subgraph. And then we paired it with some labels like structure features. And then we feed into a neural network, get an embedding, and then answer the question for the query. So here for SUREL Plus, instead of using extract subgraph or sample works, we use the node sets over here. We can use a work-based sampler or PPR-based sampler over here. And to compensate for the structure loss by reducing the subgraph to node sets, we provide a different type of the set samplers, structure encoders, and neural encoders. And to better serve the set-based representation, we designed a customized data structure here to host those sampled sets. And we also develop a sparse join operator that it can perform those joining online in parallel. So actually, the first question we want to answer here is to how we can efficiently store and access those sets over here. So here is the example. So we have a set-based subgraph with just a bunch of set and their corresponding encodings. Here I use the RPE as example. So basically, we borrow the idea from the compressed sparse row format over here. And we use this data structure to store these sampled sets. Basically, it contains 3 arrays. So the first one going to store the size of the set over here. So the difference between those 2 values are the size of this set. And then we use another array to store the indices that have of those set elements over here. And the last array is to store the encodings. Basically. So we also observe that in practice for the landing probabilities or landing counts over here, we find out that there are a lot of duplications, like a lot of nodes share the same encodings. So basically we introduced our 2-level indexing over here to further reduce their memory footprint. So basically, so here together, we stored our set-based subgraph in the data structure we call SPG. So the next question is to how to perform the join on those sampled node sets. So which is equivalently to the outer join operator in database. Okay, so here we use the nodes index as a key. And if those key appeared in both sides, we append their values together. Okay, if the key only appeared in one side, but missing another side, we filled the other side with our default value or missing value over here. So as you see, the join of these 2 sides is the result here over here. And also we need a join their corresponding structure features as well. So it is here. Okay. So we designed our sparse operator to perform the set join on those SPG objects that we mentioned in the previous state structure through some arithmetic operations. So first, it's going to perform the add operation between those two sparse rows, U and V here. And we obtained a mask. So this mask actually is the union of set SU and SV. So next, we're going to apply this mask back to the row U and row V individually to select the elements from the mask that is non-zero. So this way, we're going to retrieve the elements corresponding to the union set, basically. So the last step is if we use is to just index those non-zero elements out, then we obtain the final result. So here, for demonstration, I put a 0 over here, but we store this in a sparse format. Technically, there's 0 is never physically stored in memory. So they only appeared those non-zero elements over here. If we use the two-level indexing, then we basically going to, those results are just the indices of those encodings. So we can use these indices to gather their values from their encodings. So by this way, we can convert the set join operation to a bunch of arithmetic operations, like which is deeply optimized and have the strongest hardware acceleration. And then the readout is over here. Okay, so putting it all together, this is the SUREL plus pipeline. So basically, first, very similar to SUREL is it perform the preprocessing. So that is to decompose the subgraph to know the neighborhoods and the corresponding structure features in SPG format. So here I use the example of a set sampler of a PageRank-based. So this is the PageRank vectors of each node is sampled. So here we use the top K nodes for each sampled node over here. And so giving a query, now it called the sparse join operator. Then it's going to assemble those node level subgraph back to the query level here. And lastly, we use a neural network to encode those joined set-based subgraph and generate its representations for model serving the targeted query. So through exploring the sparsity of the data, and also we use some technique of parallelization and load balancing, SUREL Plus further improve the scalability and the efficiency of SGRL on large-scale graphs. So we evaluate our proposed framework and other baselines in the same task of SUREL. But at this time, we introduced two more data sets. The first one is a recommendations data set from SUREL, that is to predict the click-through on the online ads banners. So it's an application for recommendation systems. And also, it is the first time for us, we introduced the Twitter data set. This is the first time that subgraph-based models is developed to a billion edge graph. Lastly, we tried our model on two biology data sets of a protein-protein interaction and brain vascular network to explore the potential of the subgraph-based model for scientific discovery. So from those two tables, table 3 is a link prediction, relative prediction, and high order predictions. So we can see that subgraph-based models outperform the canonical GNs on these 6 link prediction tasks, especially on those two biological data sets, PPA and Vessel. So within the SGRL models, SUREL Plus achieved comparable performance to SUREL and outperformed the SEAL. Okay, and for prediction of the high order and relation types, we observed additional 2 to 13% of performance gain from SUREL plus to SUREL on those 3 or 4 data sets. And of course, there's a large gap between the canonical GNNs and SGRL models, particularly in these high order cases. And in terms of the runtime and memory consumption, SUREL Plus offer a reasonable training compared to canonical GNNs. It shows 3 to 11 times speed ups across all data sets in inference compared to the current soda framework SUREL. And we achieved a 20 times speed up to the SUREL model over here. And we also achieved a comparable or even lower RAM usage than the canonical GNNs. Compared to SGRL models, it saved up to a half of the RAM with a lower usage of GPU DRAM. So here I want to point out that the key point why the SUREL Plus can scale up to a billion-size graph is that we use those set-based representations with the sparse design. For the like a SUREL in this case, actually it got out of memory for those Twitter data set, which have 1 billion of nodes. So it is not feasible on this case. So this figure shows the profiling of different sampling strategies for offline processing. And we achieved like 7 times, 3 times, 4 times of memory saving on those 3 OGB data sets of storing the set-based representation. And this figure showed the sparse join achieved much better scaling performance compared to the hash-based work join on multi-threading. Okay, so this concludes the work of SUREL Plus. Any questions or comments on this one?
What was the hardware used here for the training and the inference part?
We used the NVIDIA A100.
Okay, a single one?
Sorry, what? CPU is AMD's AMR. I'm not sure the configuration, but we mentioned it in the paper's environment setting. We use the same threads for both method and all those same hardware configuration across different baseline models. Yeah.
Cool, cool. So the GPU was the A100 80 gigs one?
Yes.
Okay, thanks.
Okay. If there's no questions, lastly, I will going to quickly go over our recent work on hash-based MPN for scalable structure link representations. So for link prediction, actually, we mentioned there are 3 main approaches to do that. That is, one is called the link prediction heuristics, like a common neighbor, resource allocation, academic ADA. And there another type is the labeling trick, which is the subgraph-based model. And then there's the new type of model that is trying to achieve a trade-off between them. Basically, they are estimating those structure features. So here we have a key observation that all those type of models can be unified under this equation over here. So it's basically we are trying to give a score function between 2 nodes. Those score function is defined on the neighborhood of those 2 target nodes with some set operations between them, and we have a neural encoder on top of it. So for example, for the link prediction heuristic, we can see that for common neighbors, this is actually the union of the intersection of the node use neighborhood and node with neighborhood. Here we just count how many elements over here. So basically they're just 2 for in this case. This is a common neighbor score function. For resource allocation and AA over here, is just introduce the node degree over here and change the function from 1 to 1 over x and 1 over log x over here. And actually, we can also interpretive labeling tricks in a similar fashion. Because like labeling trick, if we use the shortest path distance, that example, that is, we have a subgraph for node U, the blue one, and a subgraph for node V, the red one. We actually doing the union of those two graphs together. And the label here is just the distance from U and from V for each node in those subgraphs, basically the distance function over here. And lastly, this new type of approach that is called subgraph sketching is trying to achieve a trade-off between the link prediction heuristics and the labeling tricks by estimating the high order neighborhood intersections and difference via hashing. So as you can see that those three approaches here are sharing the same facts, that the key point is the neighborhoods and some set operation between them, and we define a function on top of it. So this is our observation. But what's the bottleneck over here is that first, we need to obtain those neighborhoods. And secondly, actually those set operations are really costly over here. So for the subgraph sketch, that approach is using the hash-based method min hash and haplog to estimate the Jaccard value, which is the intersection over the union. And they're using haplog to estimate the union. So basically, they don't use a subgraph. They just using hashing-based method to estimate those two values. But the problem of this type of method is that they require a higher space and computation to maintain a relatively satisfying estimation quality for those values. And also it is fixed to estimate the intersection and the union of the set. So basically it only can support two set operations. So here we are thinking about whether there are another way we can achieve it. But in this time we can support more operations. And maybe here we can give some better quality, like estimation guarantees. So we came up with, there is a data structure, a probabilistic data structure called a Bloom filter, which is used for set membership testing. So what it do actually is that it uses a hash function that is going to map all the node into a space of n. So n is a very small number compared to the number of nodes over here. So, but basically what it do is mapping each node into a short binary like encoding here. We call it as a signature. So basically for each node, we put a certain hash function, and after that it maps to a value. Then we set the value of that position 1. After this, we compress the node neighborhood into a binary encoding over here. So through those encodings, actually we can estimate the set cardinality, basically how large is the original node neighborhood. And also the benefit is we can also estimate their interactions, like intersections between them, by just merging those two encodings together and through this formula. So the better part is that because the mapping mechanism is just deterministic, we already know that. So basically, we can actually give the guarantee, the error bounds of that estimation. So its estimation quality actually is depend on the sparsity of the original neighborhood. And in fact, we proved that these Bloom signatures are capable of estimating any type of overlap-based heuristics. Like we can also estimate the cosine similarity between those two neighborhoods, and we can also estimate the containment scores between them. This is just the deterministic of score functions. We can also use a neural network actually to encode those two Bloom signatures. Actually, we get some data-driven score functions, which is more expressive and powerful on top of it. So here is the overview and how we use the Bloom signatures obtained to boost the performance of MPNNs, message passing neural networks. So basically, the similar fashion that for each node, we're going to map it into map its neighborhood into a binary vector here, and then after that we use this short binary vectors. We call it the Bloom signature to actually act in two ways. Either we can use it to estimate overlap-based heuristics, like common neighbors, cosine similarity, or contaminant score, or we can use it for data-driven parallelized relations by the neural network. So how we actually use it is that we know this is the message passing formulation for the MPN. We can do is that we plug in these pairwise relations inside of it to control the message passing, basically as an edge weight. So in this way, the weight over here either can be the concatenation through a mapping, or can be the two norm of the distance between them. So, or we can use is that we obtain the embedding already, and we can plug in as an additional feature over here, and using neural network to capture the data-driven based heuristics. So through this way, combine those two things together, we can achieve the first scalable, because it's just a bunch of binary encodings, and the estimation of it is just the bitwise operation. And secondly, we can still combine with the GNN network to perform message passing on top of it. So this is the overview of this one. In terms of the performance, we can see that it have the comparable or even better performance than those subgraph-based models and the previous state-of-the-art body model. In terms of the runtime, we are actually 18.5 to 200 times faster than SEAL, and we achieved the overall speed up of 3.2 times towards body on the largest data set citation over here. And also we try to look into it, how the estimation quality of those structure features can affect the performance. So basically, we find out that using the Bloom signature to estimate the first hop and the second hop neighborhood intersection, which is the common neighbors, on the random graph, we can achieve around 2.8 to 68 times lower error than subgraph sketch. And on real-world graphs, on the OGB datasets, we achieved 12 times to 300 times lower estimation error in terms of the first hop and the second hop common neighbors. And in terms of throughput, we achieved like 41 times of and around 9.5 times higher than subgraph sketch on the CPU and on GPU to compute those hashing signatures and also estimated them. Okay, so to summarize here, we proposed the three novel frameworks for subgraph-based representation learning on large-scale graphs, adopting algorithm and system co-design. And it provides the next generation of the subgraph-based models. We have work-based, set-based, and hash-based, and it achieved the state-of-the-art performance on three types of graph benchmarks with greater efficiency and scalability. And we also showed that they have the capability and the great potential in recommender systems, scientific discovery, and many other multi-node tasks. Okay, thank you, everyone. If you're interested in our work, please check our papers. And our code is publicly available on GitHub. For any questions, please feel free to reach me, or you can ask now. Thank you.